Hello everyone, Mr. O here. Today I'm going to walk you through FRQ Topic 3, Graphic Analysis. So we are going to look at this particular topic and how it relates to the AP test, what do you expect to see, and so on and so forth. It's time to make myself little and we can go over some of these things, these key bullet points. So here we are. So the graphic analysis, and here are some things you should be able to do. Read information about the function from the graph of the derivative. So this is often how they show it. They show the graph as a derivative of some function, and you have to interpret what that means. This may be approached as a derivative technique or an anti-derivative technique, and we're going to talk about a question in a minute. I'll tell you what that means, how that relates. Find where the function is increasing and decreasing. Find and justify extreme values. First and second derivative tests. Closed interval test, aka the candidates test, testing the endpoints if you're looking for absolute extrema. Find and justify points of inflection. Find slopes, second derivatives, accelerations. So depending on what they're asking for from a graph. Write an equation of a tangent line, very important. That's always a highlight of AP and calculus in general. Evaluate Riemann sum using geometry. Okay, and then the fundamental theorem of calculus. Evaluate the integral from the area of regions on the graph. Okay, if you're looking at just the area of the different regions, we're going to talk about that one in a minute too. And then the fundamental theorem of calculus, the function g may be written as an integral. So g is defined as, some initial value that you know, and then the integral from that value to any other t value of some other function f, for example. And so this is a very popular way to see this. But I just want you to understand, this is the initial condition, and this is the derivative of g. So when you integrate the derivative, then you get the change. So here's your initial, here's the change, and we get our new value of g. And so here we have it. Then if this is the case, then g prime is f, g double prime is f prime. And again, we're going to talk about this in a moment. When we start on our first problem, and the first problem is going to be from the 2012 test. Non-calculator problem. This is number 3, and so we'll read through the question, and then we will answer these parts. So follow along with me. As always, if you have questions on these, please feel free to contact me. Happy to help. Something like this is just so much fun. So here we go. What is this? Oh, that's the bottom of the next graph. All right, here we go. Number 3. Let f be the continuous function defined on -4 to 3, where f, consisting of 3 line segments and a semicircle centered at the origin, is given above. Let g be the function given by g of x equals the integral from 1 to x of f of t dt. All right, so this is telling us, this information is telling us that this graph f is the derivative of g. That's what it's telling us. So we're looking at a derivative graph for g. And so all of our information we're going to put here needs to be related. This graph is the derivative, and if I were to integrate, I would get g. So first of all, find the values g of 2 and g of -2. So let me grab some paper here. I'm going to fold this up so you can see the graph. The folds are getting better. Here we go. All right, here's our graph. So first of all, they want to know what is g of 2. We're doing part A. Now don't get points off on messing up your geometry here, ladies and gentlemen. So g of 2 is, we're just going to figure out this information right here. What is the area from 1 to 2? Because g of 2 is equal to the integral from 1 to 2 of f of t dt. Right? So we integrate from 1 to 2. That's it. Now, they said this is a line segment. So some people, they might think, well, what the heck is that y value? We don't know. Well, if we know from 1 to 3, we've gone down 1, and it's a line, that means I must be down a half. So we're going to use geometry, 1/2 base times height. Our base would be 1, and our height will be a half. Base is 1, height is a half. Now what else do we know? We know that we're integrating from left to right, and this is below the x-axis. Therefore, a negative. So integrating from left to right, this is below the x-axis, so this will be a negative 1/4. Okay, negative 1/4. And then the second part of that, what is g of -2? Now this time we're integrating backward. We're starting here, we're going to integrate backward this way. So this area will be, go ahead and say it out loud, this area will be positive or negative. So that's we're integrating backward. That's right. This will be positive area. And this one here, since I'm integrating from all the way to -2, this area will be negative because I'm integrating backward. Okay, you can maybe barely see that at home. All right, so let's try this. So the integral from 1 to -2 f of t dt, we know this area, it's a semicircle, they told us. The radius is 1, so 1/2 pi times r squared. R is 1, r squared is still 1. Minus, because we're integrating backward, this is going to be a negative area. And this is going to have a base of 1, a height of 3. So we do 1/2, 1 times 3. And I put minus here because this is going to be a negative integral because we're integrating backwards. So pi halves minus 3 halves would be a good answer. Check, check. Okay. So that's part A. Let's look at part B. B. For each of g prime of -3 and g double prime of -3, find the value or state that it doesn't exist. So they're trying to trick you with that second part. I'm telling you that right now. All right, first of all, let's start off with g prime of -3. What is g prime of -3? Well, we already discussed this. The f is the derivative of g. So this is just f of -3. So if this didn't exist, that would mean there would have to be a hole in this graph. So it definitely exists. G prime of -3 is f of -3. And what is that? Well, we just got to figure it out. So 1, 2, 3. -3 will be on here. And because this information is going to be relevant, I'm going to use the slope formula to figure out what is the slope. Because if you know this slope, then you'll know how much are we going down, how much are we going over. We can get the exact y value there. All right, so let's use a little bit of slope formula here. The slope in that region is going to be, I'm going to take this point to this point. So 3 minus 1 over -2 minus -4. And everyone would agree this is 2 over 2, which is 1. So slope of there is 1, which means if I go down 1, I'm going to go over 1. And so at -3, my y value is 2. So my derivative of g, which is f, at -3, -1, -2, -3, is a positive 2. And how about the second part of that, which is g double prime of -3? We need to use that exact slope because now we're trying to find f prime at -3. And the derivative is the slope of the tangent line, and since that is a line, it is just the slope. So that slope is 1. We just found it right here. I would ask what questions you have, but this is not live. So I suppose it wouldn't matter what question you have at this point. You could always message me. That would be a good choice. C. Find x coordinate of each point at which the graph G has a horizontal tangent line. Horizontal tangent line. I would say G has a horizontal tangent line when the G prime equals 0. When G prime equals 0. Okay. Well, how's that relevant? Well, when G prime equals 0, f equals 0. F of t equals 0. All right, so where does that happen on our graph? Oh, there's one. -1, +1. There are two locations. This is when x equals -1 and x equals +1. All right, so first find the x coordinate of each point where the G has a horizontal tangent line. Done. For each of these points, determine whether G has a relative minimum, relative maximum, or neither a minimum nor a maximum at that point. Justify your answer. So let's start with x equals -1. At x equals -1, what do we notice? Well, the F graph that we're looking at changes from positive values to negative values at this point. So what do we have, a minimum or maximum or neither? You got it. That's a relative max. Okay. At x equals 1, there is a relative max. Because G prime, which is to say F, changes sign from positive to negative. All right, and the second part of that is x equals +1. This is neither. And the reason is because G prime does not change sign. G prime is negative here, and G prime is negative here. This does not cross the x-axis. F is not changing signs, which is G prime. Because G prime, which is F, does not change sign. I'm running out of space on the screen on that. All right, there you have it. There's part C. And then let's look at D. Now they're asking about find all values of x at which G has a point of inflection. Okay, explain your reasoning. D. I see points of inflection at x equals -2, at x equals 0, and at x equals 1. Why is that? This is where the second derivative changes signs. The second derivative. So f is the first derivative. So the second derivative would be the increasing to decreasing or decreasing to increasing of this graph f. So we're increasing here. F is increasing, then f is decreasing. So my second derivative of g, which is my first derivative of f, is positive and then negative. And then here, we're negative, decreasing, and then positive here. So this is negative sign, positive here, and then it drops to negative again. So there are 1, 2, 3 locations where we have a point of inflection. X equals -2, 0, and -1, +1, sorry, got it again. So we have points of inflection because G double prime, which is to say F prime, changes signs. And there you have it. So this is the typical example that you're likely to see on the AP test. Hopefully you find it to be pretty straightforward. Let me know if you have questions. I'm going to tell you what else is available here on this particular topic, FRQ topic 3. 2014 non-calculator question number 3. 2015 non-calculator question number 5. And 2010, there's 2015. And 2010 is a non-calculated question. Don't know the number. Apologize for that. I could look it up. But we don't have time for that. So, ladies and gentlemen, I hope you're doing well out there in internet lands. And, ask me a question if you have it, and I'll be happy to answer it.